Hello. So I would like to first thank the organizers for inviting me here to give the lecture and the talk today, and thank the Institute here for accommodating us. It's really nice to be here for 3 whole weeks. I'm a postdoc in Angelo Bassi's group at the University of Trieste, and the work I'm going to present is actually a joint work with Angelo and with MARKO, who is a PhD student in our group. The people who saw me talk before probably know that I'm usually talking about what's the gravitational field of quantum matter, how does quantum matter act as a source of the gravitational field. The topic I'm talking about today is way more conservative. It's about how does quantum matter behave in a gravitational field. So for the experimenters in the audience, it's like, so instead of the usual situation, we do an experiment in empty space, right? Freely floating. We ask what happens if we do our experiment on the surface of a planet, say Earth. As an introduction, I would like to show this cube of fundamental theories that's very often presented in the context of quantum gravity. This is a slightly modified version, but I think it's also very fitting for this topic to just see where we are and what we are talking about. So you can think of the theories that we have at the moment, the fundamental theories, as somehow, emerging from our classical mechanics by, like, in a very loosely sense, speaking very loosely, by switching on these fundamental constants, h bar, g, or 1 over the speed of light, right? So this way you end up with quantum mechanics when you introduce h bar, or Newtonian gravity where the gravitational constant matters, or special relativity if the velocities become comparable to the speed of light. And then we can try to unify these different theories. So we know that if we combine Newtonian gravity with special relativity, we end up with the theory of general relativity. Or on the other side, if we have both quantum mechanics and special relativity, we need a relativistic quantum field theory to describe this. And then the question is, what is at this outer edge of this cube, where both quantum field theory and general relativity become relevant, right? And so, of course, usually one would put quantum gravity here. So whatever the theory is that we are searching for. But for the sake of what I'm talking about, so systems in external gravitational fields, what matters here is essentially how do we describe quantum field theory on a curved space-time. And so, of course, there are a lot of people working in quantum field theory on curved space-time. There are a lot of amazing results in this field, but still it's a theory that's, like, mathematically very complicated. So if we want to describe the heavy quantum stuff that like Hendrik has in his labs with the levitated particles, or the molecules that Markus Arndt has in his interferometry experiments, then it's not clear how, like, describe this in a quantum field theory setting. So what we know, of course, and what is experimentally tested is Newtonian gravity together with quantum mechanics. That's the famous cow experiment where we have neutrons in the gravitational field of the Earth at non-relativistic level, and then similar experiments with atom fountains, or that study the eigenstates of neutrons in the gravitational field. And Now, the question that I want to discuss here in this talk is what happens if we go like a little bit along this line, right? And basically take relativistic corrections into account. So what's the right way to introduce these type of corrections? And once again, so we're only discussing the effect of an external gravitational field on quantum systems. This whole talk is motivated by a recent series of works by the group of Czesław Bruckner in Vienna, where they study the effects of gravitational time dilation on quantum systems. Particularly a very recent publication, Decoherence due to gravitational time dilation, that caused actually a lot of discussion. So on the one hand about whether this agrees with our known principles of physics, like in particularly the equivalence principle. So there have been several articles on that, and then the question if this is actually decoherence, if it is experimentally relevant with applications. And what I want to focus on here in this talk is, on the one hand, the difficulties that occur when we want to discuss center of mass motion in a relativistic context. And on the second thing is what is if we also consider an external potential that keeps our particle from falling. So as a first step, let me quickly review the way this discussion of time dilation was presented. So the idea is basically you have a clock. A clock is, you can take a quantum system that acts as a clock. So it's described by some internal Hamiltonian that just has a usual non-relativistic time evolution. And now if you have another clock that is following some different path in the gravitational field or just an accelerated curve in empty space, then the point is that I can always go to the co-moving frame of my clock, and the proper time in this co-moving frame is then the time that's actually, the proper time of the clock is actually the time coordinate in this co-moving frame. So I can describe the time evolution of this clock by the proper time along this curve of the clock. So if I compare those two clocks after a certain that have traveled on different paths, then I will see a time difference that's exactly the difference in proper time of these two paths. And now the question is, what happens if instead of taking two different clocks, I take only one clock, but bring it in a superposition state? So, and the proposal there is basically that I get a phase difference that, corresponds to this proper time difference of these two paths. So, in the sense which we just talked about, that basically means that for the one part of the superposition of this particle, I go into the co-moving frame along this path, while for the description of the time evolution of the other part of the superposition, I go into the co-moving frame of this other path, which is, of course, a very plausible assumption to make, but it's, yes, of course. At a non-relativistic level, yes, but I want to discuss. I wouldn't call it. I'm not sure if you can call it. You can of course discuss it as the proper time difference when you take the MC squared into account, right? But the Cow experiment you can derive in a completely non-relativistic way. You don't have to talk about proper time there. You just introduce the Newtonian gravitational potential as a regular potential mgx, and you look at the phase difference because of that's due to this. Well, with the, yeah, okay, with the car experiment, it's actually a bit more complicated because you have the crystal. There is a paper by Greenberger. So basically, if you want to discuss it from the point of view of the equivalence principle, and you're in the free-falling frame, then the effect is not due to the gravitational field. The effect is actually due to that you have the reflection on an accelerated crystal in the car experiment. But this is not what we are talking about here. No, there is a paper, there's an analysis by Greenberger, but we can discuss later. So yeah, so okay, so the question is basically, okay, yeah, so is this assumption a correct model for our quantum system? And it's important to point out that this is at this point of view a pure hypothesis. There is no experiment where relativistic corrections to superpositions of particles in the gravitational field have been experimentally tested. All that has been tested is a Newtonian gravitational field with particles in superposition. So if one takes this argument seriously, then what you get for a single degree of freedom, so what you typically would assume is a clock, you have your clock ticking with some frequency, and you get oscillation in the visibility of an interference pattern. And now the point is that if you add many degrees of freedom, you have not just one clock, but you have like a complex system that has a lot of internal degrees of freedom. Those will all tick with different frequencies and add together in a way that the recurrence of the coherence of the wave function becomes very rare. Okay, the very straightforward and naive derivation of the Hamiltonian that gives this effect is you just take the non-relativistic Hamiltonian for a single particle. So you have p squared divided by 2m plus mgx by the gravitational field. And then, of course, you can have relativistic corrections, but those turn out to not really be relevant. And now what you do is you simply replace the rest mass energy, mc squared, by mc squared plus the internal energy, or the internal Hamiltonian. And then what one obtains is a total Hamiltonian that is the center of mass Hamiltonian, together with a coupling term that couples the internal Hamiltonian to both the non-relativistic kinetic energy and the non-relativistic gravitational energy, mgx. So I get a coupling of internal degrees of freedom to center of mass degrees of freedom. So now I want to discuss what that means from the point of view if you talk about center of mass coordinates and try to give a more rigorous derivation of this Hamiltonian. So first of all, it's important to point out what's the problem if you want to talk about the center of mass of a composite system in a relativistic context. Which is that it's not really clear what the correct definition of center of mass is. So first of all, if you take the Galilean center of mass, so you just take the spatial coordinates weighted with the rest mass of the particles, then you get the center of mass coordinate that first of all is not at rest in a frame in which the total momentum is zero, and more importantly, this center of mass coordinate will, even if you have no external interactions, if you have only internal interactions, will in general not have a uniform motion, which is clearly not what you expect from a center of mass coordinate. So there are typically three types of relativistic center of mass coordinates, which is the so-called center of energies. That's where you simply replace the rest mass by the total energy and weight the coordinates with the energy. But this definition has the problem that, first of all, it's non-covariant. So the curve that you get for the center of mass coordinate does not transform covariantly between different frames. And it's non-canonical, so these coordinates will not have the canonical Poisson bracket relations. So the second possible definition is the center of inertia, which transforms covariantly. So it's basically defined that way. You just define the center of energy in a frame with zero total momentum, and then translate it to other frames by Lorentz transformations. So while this transforms covariantly, it still does not have canonical commutation relations. And the third definition is the center of spin, which is essentially something like the mean of the first two definitions, which has canonical commutation relations, but therefore does not have the covariant transformation anymore. So if we want to do quantum mechanics, of course, we need, in order to make sense of the notion of quantization, we need the canonical commutation relations. So we would like to actually go with the last definition. And there is a prescription by Krajcik and Foldy from 1974, who basically give a perturbative algorithm to construct these center of mass coordinates, like order by order in 1/c². And the idea is that, so you start, if you have the Galilei group generators with their algebra, then you see that if you choose the well-known Galilean center of mass coordinates, these generators actually assume a single particle form. So the generator of space translation just is the total momentum, and the time translation generator is just the non-relativistic total energy. And now one can try to generalize this to the Poincaré group generators. So if we look at the Poincaré group, then there are two commutation relations that change compared to the Galilei group. And for the single particle form, one requires that the energy takes the usual energy momentum relation, including the internal Hamiltonian. And now the task is basically to search for such center of mass position and center of mass momentum, as well as relative coordinates, that these generators take exactly these forms. And this is done step by step by first introducing a unitary transformation, which maps the Galilean variables to relativistic variables. Then one can obtain this transformation order by order in 1/c². So at the lowest order, one gets something that depends on the center of mass. So the Galilean, depends on the center of mass coordinate and momentum, as well as the relative coordinates. One obtains the form of the internal Hamiltonian in these coordinates. And finally, by simply expanding the Poincaré generator, one obtains the center of mass Hamiltonian in these coordinates that are found in this way, which unsurprisingly is exactly the form that one expects from a relativistic expansion of simply a relativistic expansion of the energy momentum relation. So one has the rest mass energy term, the non-relativistic terms like the non-relativistic kinetic energy and internal energy, and then the first order relativistic corrections have the kinetic energy correction, the correction to the internal Hamiltonian, and the coupling term that couples the kinetic energy to the internal Hamiltonian. So this is all in Minkowski frames still. So now the question is, how can I translate this prescription to non-inertial observers or to an observer in the gravitational field? So first of all, this is simply the equivalence principle, but if I have, if I have an observer in the gravitational field, or I have a world line somewhere in the gravitational field, and I want to describe the physics from the point of view of a co-moving observer, then I usually do this by using Fermi normal coordinates. And if now one goes to the special situation of an observer that's hovering at a constant altitude, or for example, an observer that's on the surface of Earth, then these coordinates take approximately the form of the Rindler spacetime. So basically take the form of an accelerated Minkowski frame. That's really just the expression of Einstein's equivalence principle in general relativity, that a homogeneous gravitational field is equivalent to an accelerated observer. In order to discuss how to transform or how to describe the situation we had before in terms of the perspective of this accelerated observer or this Rindler observer, we can discuss how the killing vectors, how the time-like killing vectors that generate time translation in this space-time are transformed to the local Lorentz frame, the instantaneous frame with the observer, and what you get is this relation. So the time-like killing vector for the Rindler observer, so for the global accelerated frame, is 1 plus gx divided by c squared times the killing vector in the local Lorentz frame. And excuse me. This is at t equals 0. At t equals 0, the term dx has a time in it, right? Okay, so yeah, but at t equals 0. Yes. Thank you. Okay, so and then we can basically, by analogy, so we want to know what does the time translation generator look like, so in the Rindler frame or of the Rindler observer look like in the co-moving Lorentz frame or in the instantaneous Lorentz frame, and by this analogy, so we can either represent the Poincaré generators in by the killing vectors or by operators on our Hilbert space, and so basically we go to the Hilbert space representation by this analogy, or by looking at how the killing vectors transform, and we get that the Rindler Hamiltonian is just the Minkowski Hamiltonian plus g divided by 2c squared, and then the anti-commutator of x with the Minkowski Hamiltonian. So I write that completely, then I get that the Hamiltonian for the Rindler observer is just the Hamiltonian in flat space plus the usual gravitational term, the non-relativistic term mgx, plus relativistic corrections that where gravity, so where you have one term that is xp squared, so just center of mass dependent, and a term that couples the internal energy to the position via gravity. And that's exactly the Hamiltonian that we had given before, which is so basically now the Hamiltonian of this so defined center of mass coordinates and has exactly this coupling that we observed of the internal Hamiltonian to, to the center of mass position. So far this was all nice, but this was without any external interaction. So basically what we discussed so far is what is the motion of a free-falling particle in the gravitational field seen by an accelerated observer. And now we want to ask what happens if we have a particle that is at rest in our lab frame, so a ball lying on a table. And if we look at that classically, then we can just take the Hamilton equations of motion. So you require that the momentum of the particle doesn't change. That's basically the requirement that it's lying on the table. And what you see is that, of course, your external potential must be such that it does not just cancel the non-relativistic gravitational term, mgx, but it must also cancel the relativistic corrections of this term, so the coupling of internal Hamiltonian. Or if you would go to higher orders, then of course you must basically cancel your gravitational effect to all orders in 1 over c squared and not just to lowest orders. So what does that mean for our quantum system? Well, we can, the most conservative way to talk about a particle that's sitting on a table is to just take Ehrenfest's theorem and require that the expectation value of the position is not accelerated. And if you now require that you have a potential that is just position dependent, so a v of x potential or u of x potential, then you get a requirement, or then you find out that in order to satisfy this condition, the potential must have this form. And in general, if you don't have a stationary state, this will be a time-dependent potential. So basically, you have to tune this, this potential to both the internal and the external energy of your particle. And if you take that seriously, then the resulting coupling term that you would get is still gx, but now not coupled to the internal Hamiltonian, but actually coupled to the difference between internal Hamiltonian and the energy expectation value of the internal energy. However, so if you just as a classical analogon again, if you look at, for example, a classical Klein-Gordon field that is minimally coupled to an electromagnetic field. So basically you just replace IH bar dt by IH bar dt minus E times electric potential. And you get the Schrödinger equation with 1 over c squared correction terms by simply expanding the Klein-Gordon equation in terms of 1 over c squared. Then you see that you can write this Schrödinger equation with the usual kinetic energy term and the relativistic kinetic energy correction plus the potential. And this potential, in this case, is not just position dependent. So you have E phi and E phi squared, but you also get a term that depends on the momentum. So in general, if you have a relativistic correction to the interaction, you get momentum-dependent terms. And now, if you do the same in the quantum case, and you say that your external interaction is some operator that depends not just on position, but also depends on p, but this time no time dependence, then what you get is that the only way to satisfy this condition that the expectation value of x is not accelerated is you have this external potential which exactly cancels all the gravitational terms in your Hamiltonian, right? So the result that you get is relatively unsurprising, probably, is that if you have an external potential that keeps the particle from from falling, then this particle will just evolve with the free Minkowski Hamiltonian, plus eventual terms that depend only on momentum. Yeah, so I still have some time, but I'm already at the end. So the conclusion is just a summary of what we find. So of course, if you have a Minkowski observer, so an observer that's just floating in empty space, or a free-falling observer in the gravitational field of the Earth, you don't have any coupling of internal energy to center of mass motion. So you don't get any effects from that, also no decoherence effects. On the other hand, if you take an accelerated observer, so here the observer in an elevator that watches the free-falling particle, or an observer standing in the lab on Earth, watching a free-falling particle, for example, doing an interferometry experiment with free-falling particles, then in this case, indeed, you get a coupling of center of mass degrees of freedom to the internal energy. You can, of course, look at the opposite situation. So you can say, okay, take the free-falling observer, the Minkowski observer, but look at a particle that is supported by some potential that keeps it from falling. What you will get then is you will get a decoherence effect from this potential. So again, in this case, you will have decoherence, you will have coupling of center of mass to internal degrees of freedom. And finally, and that's the situation that's most interesting for the sake of the discussion, and which was actually not considered correctly in the papers that I cited before. If both the observer and the particle are accelerated, or equivalently, if both the particle and the observer are at rest in the gravitational field of the Earth, then excuse me, then the coupling that's coming from the Rindler observer Hamiltonian and the coupling that's coming from the external potential will just cancel each other completely, and again, there will be no decoherence term in this case. Okay, so that's the results, and yes, I thank you. And again, so this was work that mainly Marko, PhD student, did together with myself. Thank you.
So we have time for questions.
Why would you expect a compatibility of your results with the equivalence principle if you chose a scheme to define the center of mass that was not covariant?
Well, the point is that, so, yeah, okay, I don't need the slide for that. Because everything I do, the whole derivation of the Hamiltonian, does not depend on the coordinates, right? So the coordinate of the center of mass is something that is frame dependent, but the form of the Hamiltonian is not. Okay, so you can go if you go to another frame, you will have this center of mass coordinate that is described by this Hamiltonian will be a different coordinate in this other frame, but the Hamiltonian that describes the time evolution of your quantum state, that describes time translations, has the same form in these.
But I thought the full point of not being covariant is that your result depends on the initial choice of the frame in which you do the calculations.
You have to be careful what depends on the choice. I'm talking about the center of mass coordinates. The coordinate that you define in this way, the R and the P, will be something that does not transform covariantly between different frames. But I'm not interested in the form of R and P. What I want to know is what is the time translation generator? What is the Hamiltonian? And the time translation generator will have a certain form in terms of R and P, whatever R and P are. Okay, so what I know is there is, in any frame, there is some R and P in which the Hamiltonian has exactly this form. And I'm basically looking for the transformation in which this is the case. Now, yes. Yes, yes. Because the way we usually do quantum mechanics is you take the time translation generator, you take the Hamiltonian, and you apply it to your wave function, and you say, this is IH bar dt of my wave function. That's the prescription how you quantize the system. You say time translation is Hamiltonian, and you can now you need to find coordinates in which you have canonical Poisson bracket relations in order to do this. The separation of the coordinates depends on this choice, yes. Yes. Yes, but I'm not changing the frame anywhere here. If you are in a certain frame, I am. The whole derivation is coming from general relativistic consideration, right? The equivalence principle is I'm basically starting with the equivalence principle. Yeah, I think we should discuss more thoroughly. Yeah.
You canceled gravity in case when the body is sitting on the tabletop.
Yes.
You idealized the model as to introducing a linear potential to cancel gravity to all orders.
No, I did not. Maybe I wasn't clear enough about this.
Yeah.
The only thing that I require is that the second order time
yes.
of the expectation value x is 0, and there are exactly two. So okay, and now you can make so now I can make two assumptions. I can either assume that I have a potential that is a function of only position and time. Okay.
Yeah.
Does not depend on momentum, and then this is the result that I get. I don't expect that it's linear. It can be any. I have to require that it can be written as a Taylor expansion in X, but it can have arbitrarily high orders in X. I get this form of the potential, and the same is true. The same is true here. Sorry, not here. Here. So here I just require that the potential does not depend on time, but can depend on the center of mass potential. So the U is a function of X and P. And then I can take an arbitrary Taylor expansion in X and P, and I see that the only form of U that actually gives me this condition is something that looks like this, plus some arbitrary function of just momentum. That there is no assumption that it's linear or yeah.
Well, why didn't you start from the realistic situation? Sitting on the tabletop means that you are under the influence of, say, a harmonic force. So you push your system is sitting in the bottom of say, harmonic potential.
Yeah, plus
Why didn't you start less formally?
how do you introduce the relativistic corrections to that?
Okay.
Any more questions? No, so let's thank our speaker. And now it's a tea break, so see you at again 4:30.